All right, welcome to the RI seminar. It's my great pleasure to introduce Kayvon Fatahalian, who is the second in our series of 4 superstar young professors who came to CMU this year. So Kayvon is interested in computer hardware, computer architecture, and also graphics, which is my area as well, so I'm really excited about this talk. Kayvon did his PhD at Stanford, worked for Lytro for a year, and in fact, before that was an undergrad at Carnegie Mellon. So he sort of came back home. In addition to being an awesome student, he was also the #1 US tennis player, Division III in the United States.
The applause is definitely not necessary. Okay, so am I heard properly? Okay. So thank you, Adrian. So I'll get started. What I wanted to talk about today actually is the work that I do is in graphics, but it's sort of very systems-y side of graphics and image synthesis. So I do both algorithms, and then I also think about the design and the hardware architecture of GPUs. So when they invited me to talk to this crowd, I was like, robotics, and I'm doing graphics. Let's see what can I speak to them about. And I acknowledge up front that many of you in this room are not on a day-to-day basis interested or thinking day-to-day about synthesizing images. But it is probably very likely that given some of the tasks that you do on a day-to-day basis, you have come in contact with GPU processing or some kind of high-performance parallel processing recently. So I am a little curious, actually, is in your projects in robotics, maybe in vision or machine learning, have you guys worked, have you used GPUs at all in your work? Is that reasonably, some, a few? Okay. And the reason why you did was that either you connected some dots or somebody, a colleague of you told you, is that these processors that are designed to make pictures, well, they're these very, very efficient systems for making pictures. Like, for example, this NVIDIA chip today, we're rendering 16 billion pixels per clock. That's a lot of frames of HD worth of pixels. And we're processing billions of triangles. But to you, at their heart, they probably were, you thought about them as these multi-core processors. And that's probably why you use them. Is that if you think about this NVIDIA chip, you've got a 16-core processor that can provide you 1 teraflops of compute, and then it's connected up to a memory system that provides 133 gigabytes per second of bandwidth. And you use these systems for machine learning or for vision or for image processing as compute accelerators. And for those of you that can cast your particular application and structure it as data parallel computations, these GPUs have provided a very interesting substrate for you to accelerate your computations with. And you've programmed it with like OpenGL or with CUDA, and you've thought about it like data parallel programming. Right? And if you worked hard enough, these things might be, it's parallel programming, so it can be kind of hard to deal with. But if you worked hard enough, at the end of the day, you came out with some code that ran really, really fast. And by really, really fast, I mean pretty darn fast, in that people in all areas have been using these architectures, and 3 of the top 5 supercomputers today actually have graphics processors in them, not to do rendering, but in fact to accelerate scientific computing or data parallel computations. Now, I started this talk talking about sort of data parallelism, parallel programming, things that sort of many of us consider to be a little difficult to do. Now in graphics, we actually don't think about GPUs this way. Right? We don't think about this way at all. In graphics, we've come up with sort of the right high level of abstractions. And in graphics, that primary abstraction is something that we teach everybody in Graphics 101, which is the graphics pipeline, where all of our rendering computations that we use in real-time rendering, well, they're abstracted as a series of operations on a very simple number of primitives and entities. And in graphics, those primitives are things like surfaces, which are turned into meshes. The meshes are sort of projected onto a screen. We discretize the meshes to figure out what pixels triangles overlap. We end up calling each of those overlap pixels a fragment. And then we color those fragments based on simulation of lights and materials and things like that. And at the end of the day, we get these colored pixels. So this is sort of the canonical graphics rendering computation today. Now, how do you program this thing? And to program this thing, well, what do? Is I've got a couple stages. And using programming systems like OpenGL or Direct3D, you'll configure some of the black boxes. In this day and age, you actually write functions that manipulate these primitives. So you actually provide small pieces of code, which we call shaders, but in general, they're just side effect-free functions that for each vertex comes in, or each pixel that comes in, we perform an operation that computes the position of the vertex, or computes the color of the pixel. And at the end of the day, we start issuing this system commands. We say, here's a configuration, here's a program, here's some data buffers, and then here's a surface, here's a surface, here's a surface. So that is how we program these graphic systems today. And we think about these things as abstract machines. There's not a lot of whole graphics here. There's just vertices, triangles, pixels, and then a machine talking about how to transform these entities into each other to produce a final image. So in graphics, we often think about this structure we think about it as an abstract machine, much like, for example, if you run a MapReduce computation, you're using that as a structure to provide to express your algorithm in a very, very efficient way. And this structure has been remarkably versatile. So we've taken this, and this was how we started programming graphics in the early 90s. And we've used this, and we were able to do a remarkable number of things. And we've gone from the earliest silicon graphics workstations 20 years ago, all the way to these modern NVIDIA GPUs today, which combine those 16 cores that provide teraflops of performance with a bunch of fixed function ASICs in there to continue to accelerate these computations. And so by using this structure and using the domain knowledge since we know we are rendering, we were able to map these computations very, very efficiently onto these fairly complex systems. So what I wanted to talk about today was actually three quick things, and one of them I've just told you about. Was first of all is how we think about graphics, and how we think about graphics not as libraries, but we think about these graphic systems as abstract machines. And then I want to talk about sort of the research that I've been doing for the last 2 years, which is taking these machines and pushing them to the next level, trying to approach film quality, Pixar quality rendering in real time. And then I want to say a few words at the end of how this style of thinking might be applicable to other application domains. And the application domain that I'm particularly interested in is sort of imaging and photography. Okay, so despite how fast these machines have gotten, and despite how much compute power we have today, is that real-time graphics still fundamentally uses very large triangles. The geometric detail that we can render at 60 frames per second at real-time rates remains reasonably low. And you see in this scene, this is not a state-of-the-art game, but I wanted to use it as an example, is that this ground plane in this game from just a year or two ago, about Pixar's Up, is in fact, even though it's supposed to be this bumpy, high-resolution surface, it is in fact 2 triangles. It is in fact a plane. And to be a little bit more quantitative about these things, instead of just showing pictures, here's a histogram of triangle size for sort of top-in interactive applications today. And you'll kind of notice that there's 2 big bumps in this histogram. We've got a lot of triangles. We've got a lot of geometry that's roughly a few pixels to a few tens of pixels in size. And you've got a whole lot of geometry that's large. So the projected size of each triangle in these meshes continues on average to be hundreds of pixels in size. And so most of the screen is actually covered by these types of triangles. Now, what I was interested in doing is I'm interested in rendering pictures like this. Now, there's 2 big differences between this picture and the picture that I showed you. The first one is that the lighting and the shading is more complex, and I'm not going to talk about that today. But the big difference that we were interested in tackling is the level of detail in which surfaces are represented. So you see here that I have smooth surfaces, I have hair, fur, and you will see absolutely no discrete polygon artifacts in this image. And if I zoom in and show you another picture from the actual movie Up, you can see, I'll tell you, you can't actually see it, but his sweater, Carl's sweater is actually, the bumps in the sweater are modeled with geometry. And if you have a surface that's that detailed, then you can begin to perform the advanced lighting and simulation calculations on it. Now, these small polygons, these really high resolution meshes that we need to render to get this type of quality, well, we have a term for them in graphics. They're called micropolygons. And here I'm actually showing you the mesh with about a pixel is highlighted up there in the top right. So the meshes that we're interested in rendering to get the type of quality that we hope to achieve in real-time rendering in the near future basically are polygonal meshes, usually made up of triangles, where all the triangles are about a pixel in size or less. Okay. Now we don't need to go much farther than that because once you have subpixel artifacts from a visual perspective, you just don't see those artifacts anymore. Now, the question that I had was, these systems are fast. You know, a teraflop on a desktop is a lot of computation, plus fixed function ASICs. How far are we off from just being able to do this in real time? Because nobody had actually really tried. And what we found out in our research is that current GPUs actually end up being incredibly inefficient systems for doing the type of rendering that we want to do in the future. And here's what I mean by inefficient. They're powerful, but if I took the compute capability that I have now, and I have the ability to scale things up, add more bandwidth, add more cores, what would end up happening would I would have a really powerful GPU that was incredibly inefficient. It would be a bad system for rendering photorealistic graphics. So there are a couple reasons for this, and they end up being sort of very simple graphics 101 types of concepts. And they have to do with tessellation, rasterization, and shading. So let me give you a sense of what those actually are. So the first problem we had was that it was actually inefficient to provide a graphic system with these triangle meshes. They're very dense triangle meshes. They're very large. And so we need to generate them on the fly from some compact mathematical representation, so some higher order representation of the surface. Okay. And it turned out that the algorithms that existed for taking a higher order surface and turning them into triangles, the ones that produced really high quality meshes actually were difficult to parallelize. And the ones that we have in real-time rendering actually produce very, very low quality meshes. And so I'll talk about an algorithm that we came up to solve that. The next problem that happened was that all of our current hardware, all of our current parallelization schemes for rasterizing triangles. And by rasterizing triangles, I mean figuring out what pixels a particular triangle overlaps, are done with point sampling, basically finding the red dots. And we find those red dots by going data parallel across the dots. We test a whole bunch of dots, positions, against the triangle in parallel. And when these triangles ended up shrinking to about a pixel in size, well, that axis of parallelism just disappeared on me. So the whole way that we were parallelizing a major part of our computation actually was wrong. And last, and I'll talk about a little bit later in the talk, is that the actual computation of color, the per pixel color, the lighting and shading calculations, ended up being like 10 times more efficient less efficient when the triangle shrunk to about a pixel or less in size. So these were the big problems that we identified when we were trying to do this work. I'm going to talk about two of the solutions today. And the reason why I'm going to choose two of those solutions is that we invented some new algorithms and at the same time changed the hardware to be more, we changed it, we came up with new algorithms and then we came up with new hardware designs to meet the needs of those algorithms. So it wasn't like we took what we were given and tried to come up with new algorithms, and nor did we try and brute force it with hardware. We actually changed both at the same time. So let me get started by talking about this problem of tessellation. So this is one of those situations where there were two main solution strategies out there. They both had good things and bad things about them. And the solution that we came up with was obviously a best of both worlds kind of solution. So I'm going to tell you about an algorithm called Lane-Carpenter, which is exactly the algorithm that Pixar uses to render its surfaces. It happens to be a very high quality tessellation algorithm that had been around since the 80s. And I'm going to tell you about GPU tessellation that's in the cards that you see today, which is lower quality but really fast. So to set the problem up, here's our inputs. Our inputs is a higher order surface. So for example, here I'm trying to show you a bunch of patches from a surface. Those might be represented as bicubic patches or in some parametric representation. And the output needs to be a mesh that closely approximates that surface. And I would like those mesh triangles to be all about the same size. And I'd like them to all be about a pixel in size. Now, the most naive thing to do is, given the parametric domain of the surface, here's a 2D parametric domain partitioned to U and V, is to split the surface up into polygons equally in its parametric domain. And obviously the result of that is when I view the surface, depending on its curvature or depending on the camera location, I might end up with pieces or polygons that are either too big, which means I risk having artifacts, or too small, which means I've generated too many of them and I have an inefficient algorithm. Okay, so here's what this algorithm called Lane-Carpenter does. And again, like I said, this is the algorithm used by RenderMan, and it's basically at the heart of all of Pixar's movies. So what it's going to do is it's going to take a surface, and it's going to begin partitioning the parametric domain. It's going to be a divide and conquer algorithm. And at some point, the divide and conquer process is going to stop because the algorithm estimates that the surface is now flat enough to do this simple uniform tessellation. So the algorithm is a hybrid of adaptability, divide and conquer, and performance, regular data parallel tessellation. Okay. Now, the problem with adaptive tessellation ends up happening right here. It's that if I choose to break the surface down, yeah?
I was wondering, you were mentioning that it was inefficient to have two small triangles.
Uh-huh.
Is it also possible that you could create like aliasing artifacts?
You actually can, because you can oversample the surface, and then you get the other type of aliasing as well. It's usually less prone because you have a lot of ways to catch yourself, because you're going to do texture filtering and things like that that could also happen. But yeah, if you put 1,000,000 leaves in a pixel and you sample once per pixel later on down the pipeline, you're going to undersample that signal, and you in fact will get aliasing. So really what you'd like to do with good tessellation is you'd like to basically get about to be a pixel in size. It doesn't necessarily mean you're at the Nyquist rate for a super high frequency surface, but it just means that the frequency of that geometry is so high at that point, you're kind of thinking about tessellating and stopping at once per pixel as kind of a pre-filter for the rest of the system. Yeah, exactly. Okay, so here was the problem area that we had to deal with, is if we've got a surface, we break it up at different rates into different numbers of pieces. So along these boundaries, what you'll see is that the polygons that I'm creating don't match up. And if I have a piecewise linear approximation to a curved surface, the surface is going to rip apart along those boundaries. So here I'm showing you the parametric domain of the surface, the partitioning into polygons in the parametric domain, and then here's the rendered surface. And you can see how the sampling of the surface does not match up. The surface rips apart because the approximations to the curve are different, and we end up getting holes in the surface which manifest in graphics as these empty pixels, which we call cracks. Okay. Now, the sequential, single-threaded algorithm for solving these problems tends to be stitching, and stitching is essentially emitting a sequence of triangles that sort of fills in the cracks. So you have two sides of a surface, you emit some stitching geometry to fill in any kind of holes in the surface. Now the problem with this is that it creates a dependency. It means that these surfaces and these surfaces have to know about each other, and I have to communicate the information about how they're tessellated to each other, which defeats my ability to parallelize these algorithms well. Okay. Now, a major aspect of the solution here is to get both sides of a surface where they abut to actually independently compute the same tessellation factor on that edge. Okay, so here, where the surface is abutting, the idea is to use information about the parametric surface only along that line to compute a tessellation factor. Now that line, that curve on the surface, is shared. It's knowledge shared amongst both of these patches. They independently compute the same tessellation, and then we use a semi-regular pattern to connect the regular region to these boundaries. So to take a step back, we have a region. We're going to execute a computation based on the surface geometry to compute a tessellation rate, a constraint for each of the edges. And then given each of those edges, I'm going to come up with a tessellation of the surface. Now it turns out that this problem was actually, this part of the subproblem was actually a well-known problem, and it's implemented in hardware. It is the semi-regular tessellation that we have figured out how to build really, really fast processors for in GPUs. Okay, so GPU's tessellation looks very much like this. Is when you provide a surface patch to the graphics processor, you also compute these edge constraints. Out comes a mesh. And then for each vertex in the mesh, you use your standard vertex processing shaders and things like that to compute the positions of those vertices. Now what we wanted, or what we needed to come up with, was a way to adaptively partition this patch using divide and conquer into a bunch of subpatches, then compute constraints for each of the subpatches, and have all those subpatches line up at their own boundaries. So here's an example of that. So here's, again, a 2D parametric domain. We're moving along with the divide and conquer process. And now let's say at this point the divide and conquer process has gone ahead and tessellated the two left parametric regions. So the question is, how are you going to tessellate this region? And here the surface properties have set the tessellation rates, because of the detail on the surface, the 3 segments along this edge and 4 segments along the top. So there's a non-uniform tessellation due to the adaptivity. And then on the right edge, because of the surface properties, I'm just going to tell you that we need 5 segments. That is what the algorithm determines. So the question is, how do you actually meet all of these constraints? And the solution that we came up with, and we were able to show that it was not a big problem in rendering, is that you start making these cuts, these divide and conquer cuts, that you don't partition the surface in half. You actually make them in non-isoparametric directions. And so we changed the divide and conquer process to actually make these non-isoparametric cuts. And that was the key to coming up with an algorithm that was adaptive, crack-free, and also parallel. And it turns out that this algorithm, even though it is different, it produces different triangles. But at the end of the day, the triangles are very close to the triangles of the original non-parallelizable algorithm. So here I'm showing you a visualization of the triangle size for this scene, where I've tried to tessellate all of my surfaces into these small half-pixel area triangles in this case. And the image is green when the triangles are exactly a half pixel in size, and red if they start getting too small for over-tessellation. And you can see that most of the surface is green. Here the parallel algorithm is producing different vertices, different triangles, but only about 7% more vertices. And if you flip it around and compare it to an algorithm that doesn't have the divide and conquer process in it, I produce much better triangles using 40% fewer vertices, because these algorithms can adapt to the complexity of view and or the surface detail. So at the end of the day, we had an algorithm. It was divide and conquer, and we split it into 3 different phases. We split the algorithm into an adaptive phase, which actually need not be programmable, into a hardware-accelerated tessellation phase that generated the meshes, and then a programmable data parallel phase that actually computed the position of all the mesh vertices. So this is the reason why we thought this was notable, or other than just being able to come up with a better algorithm, was that we had a systems problem, but then we went back up into algorithms and designed a new algorithm to fit the requirements of the system better. And the new algorithm produced actually different results than the original algorithm, but that was okay in this situation. And it turned out that being able to relax some of the constraints, again, the ability to make these non-isoparametric cuts, allowed us to produce 1.4 to 8 times fewer vertices than the simple uniform tessellation patterns. And it had a heterogeneous implementation in hardware. So the other thing I wanted to talk about is a similar thought process that we do in shading. Now, to describe this problem for you, I have to actually set this up with a little bit of advanced graphics. And the idea that I'd like to talk about is an anti-aliasing problem, and it's called multi-sample anti-aliasing. So here what I'm showing you is I'm showing you a triangle. It's on a pixel grid. And in graphics, we're going to compute what pixels this triangle overlaps by point sampling coverage. So for every pixel, we're going to take a number of samples per pixel. And here I'm showing you the samples that lie within the triangle. Okay? And the reason why we super sample the screen is so that we get estimates of partial coverage for anti-aliasing. So here, the edges of the triangle are sort of smooth as a result of the partial coverage information coming from the super sampling. Okay? Now, these point and triangle tests are pretty cheap. And we take many samples per pixel in graphics, 8 or 16, to get a very good partial coverage estimate along boundaries. So we anti-alias lines and edges. Now, it turns out that the computations that need to be done per pixel to compute color those are the simulation of lighting and shading and materials. Those are actually much more expensive computations. And so graphics systems actually sample shading only once per pixel at a much lower rate. And the reason that we can do this, which relates to Adrian's question, how can we sample a signal once per pixel and avoid aliasing, is that texture data can be pre-filtered, whereas geometric data can be not. So in this particular example, the shading is coming from texture maps, where the texture data is pre-filtered on the right side and not pre-filtered on the left. And I'll zoom in to actually give you a closer look. Here the texture data, the high frequencies have been taken out of it. You get a much nicer appearance than here on the left. And I'll go back a slide and show you how that manifests in the actual image. So you can see basically the jaggies on the left and the lack of jaggies on the right.
But how can you, say this separately from the geometry?
So
the texture is always on a plane, so you could have needles sticking out in the geometry.
How can we say?
How much pre-filtering is required?
For the geometry or for the texture? It's a good question. Okay, I think I understand your question. But so how much pre-filtering is required for geometry? Okay. The problem is that we have solutions for pre-filtering texture data on a regular grid on the plane. In fact, here's our solution. Right. Nobody's come up with very good solutions for pre-filtering geometry. So that is the reason. So the solution, the current best known methods is to actually take many samples per pixel in sampling coverage or the position of geometry. So we super sample that because we don't have good algorithms for pre-filtering. And it so happens that taking these samples is cheap and computationally inexpensive. And then we do leverage our pre-filtering mechanisms for texture data. Okay. So this is actually one of the more important ideas in computer graphics, is to sample these signals at different rates and sometimes use super sampling and at other times use pre-filtering. Okay. So to properly pre-filter the signal, I need to know how much of a texture lands within each pixel. And we do that by computing derivatives on the surface. And in a graphic system, derivatives over a surface are taking first order differences between field values, texture coordinates, in adjoining pixels. Okay. And so in order to always make sure that these derivatives are easy to compute, pixels are generated by rasterization in 2x2 blocks. So these are the minimum granularity at which all graphics processors work. So if a triangle covers any visibility sample within a 2x2 block, we're going to actually perform 4 shading computations for that region of the screen. And we're going to use finite differences between those parts of the screen to compute the derivatives needed to pre-filter our texture data for shading. And then finally, the final colors that are produced are weighted by the overlap factor to get these smooth edges. Now here's the problem. The problem happens that when 2 triangles abut, these 2x2 regions on the border of these triangles end up getting shaded or processed multiple times. So in this visualization, I'm coloring each pixel by the number of shading computations that occur by the graphics system as a result of these 2 triangles moving through the system. And you can see that there's double shading along the boundary between 2 triangles. And as these triangles shrink to the triangle sizes that I care about, the amount of extra shading done by the system, which is largely redundant, actually increases dramatically. And in fact, if you measure it all the way out to 1 pixel area triangles, you have about 8 shading computations per pixel. And remember, the whole point of this system was to actually shade at a lower resolution or at a lower frequency than the frequency at which we sampled visibility. So the optimization that was in there for large triangles to save a lot of work is now creating 8 to 10 times more work in these systems. So the idea, or the goal was to have a system that behaved exactly like the systems for large triangles. And for large triangles, the idea is to shade a triangle once per pixel. And so the idea with small triangles from the same surface is to shade a surface exactly once per pixel, not triangles. And the solution that we came up with is a paper that we wrote last year. It's called quad fragment merging. Quad fragment comes from the fact that we're shading these 2x2 blocks of the screen at a time. We call those quad fragments. And here's how it works. So here's a very, very simple graphics pipeline like I showed you at the beginning of the talk. There's some tessellation, produces some triangles. Those are rasterized to produce these 2x2s called quad fragments. And at the end of the day, these quad fragments all go through some shading function to produce the color of those pixels. Okay? Now, the observation that we made was that in our system, unlike sort of OpenGL before tessellation, is that the connectivity between the triangles is actually known. Typically in OpenGL, you just hand OpenGL a list of triangles with no connectivity between the two. But since our system generated these triangles, we have some priors. And the biggest one is that the triangle connectivity is known. So what our solution does is it takes the quad fragments produced as a result of rasterization, it buffers them, and then it's going to stick them back together, merging them prior to shading. So the end result is that there's a change to the system right here. There's some buffering and some aggregation here. And from this point forward in the system remains unchanged. Okay, so the question is how we actually do this aggregation of shading work. So here are 4 triangles. They're produced via tessellation. They're all connected. They all came from the same surface. Here the location of 4 shading sample points in 4 adjacent pixels. And here are the locations of the visibility sample points. So the gray dots are where we sampled the coverage of the triangles. The white dots are where we're going to sample the appearance or the color of the triangles. Now, given this input, a graphics system is going to produce these 4 quad fragments. So the visualization that I'm showing you here, the mask, sort of the bit mask of 4 values per pixel is the coverage. And I'm color coding the shading sample location by not the color, but the sort of the number of the triangle that it came from. Make sense? And if we put them together, if you take the union of the coverage, and if you select one of the triangles, one of the shading samples for each of the 4 pixels, well, what do you have? You have a quad fragment that represents 4 shading samples from the surface, from adjacent triangles, and it represents the aggregate coverage of all of those 4 triangles. And then if you run your shading computation on this data structure, which is very similar to the old data structures that we have, you've done less work. In this case, the number of fragments that we've shaded by the system has been reduced by a factor of 4. Now, the challenge of doing this, the thing that made this difficult, was the question of when can you make these merges and when can you not? And let me give you an example of a case that's actually hard. So here's a triangle mesh. It's a detailed surface. It folds over on itself. So I've given it kind of a flag pattern here. And I want you to look at these pixels here that happen to be right on the border between these triangles. So the surface folds over on itself. Now, what a GPU does is that a GPU today is going to shade to generate fragments, and it's going to shade both the blue and the white triangles in these regions. It's going to weight the result by the respective coverage of the pixel, and what you're going to get is an anti-alias set of pixels along this edge. Okay, so that's what happens today. Now, if I do exactly what I just told you, and in fact I choose one of the triangles within each pixel to shade, I'm either going to end up with a result that's all blue, or I'm going to end up with a result that's all white over here on the right side of the screen. So I've defeated the multi-sample anti-aliasing mechanism of GPUs. So the trick is to only merge quad fragments from adjacent triangles. And again, this is where the information about the mesh and the connectivity comes in. And it is not a good thing to talk about here, but it turns out that we came up with with a very, very simple way of detecting, of storing, representing, and then checking connectivity. And we can determine if 2 quad fragments can be merged with some simple bit operations. And if you only buffer 32 of them, you can actually get 90% of all possible merges that the system can legally perform. So we came up with an algorithm that could be implemented very, very easily in hardware with very, very low cost. And as a result, this is what happens. So here's a graph of the number of shading computations per pixel as a function of triangle size. And so we've been talking about the far left side of the graph, way out here, for pixel or just under subpixel area triangles, turning this optimization on reduces the amount of shading work in the system by more than a factor of 8. And in graphics, lighting and material simulation is the bulk of the workload, so this tends to translate into overall system performance very directly. And even if you go all the way out here to 10 pixel area triangles, very much like what we're working on today, we were happy to see that we actually can still provide a 2x benefit to the system if you turn this optimization on. And the results are that if you respect connectivity correctly, these two images should look more or less the same because they are. And if I actually gave you a numerical diff, I'd have to amplify the numerical diff by, I think, a factor of 10 to actually produce color in the diff that you could actually see on the screen. Here's another example of the type of surfaces that we really care about. It's both very shiny and high frequency. And you will notice differences. The output is different. Oops. But the two images look very, very similar. And the one on the left has about 8 times less computation going on. So what I just talked about was, I talked about an optimization that reduced the cost of shading these high-resolution meshes. And the main idea was to shade surfaces once per pixel, which is sort of a logical transition from the previous method of shading triangles once per pixel. But one of the key points is that, again, there was domain knowledge used to come up with a better algorithm to better parallelize and come up with a more efficient parallel system. And the algorithm that we chose took the workload, all these independent fragments, and mashed them back together so they looked and could be shaded just like the previous workload. So it was a complete augmentation of existing systems. And so those data parallel cores, those 1.5 teraflops, did not have to change to actually make these optimizations work. So as a result of this thinking, here's what happened. Is I started this talk talking about the graphics pipeline. And I told you that this graphics pipeline was our architecture in computer graphics. And it's something that we hold on to very, very closely. We're very unwilling to change it, much like Intel is unwilling to change x86. It is the architecture that we build on, right? So I told you that this architecture began to break down under future graphics workloads. And I told you about 2 algorithms, that new algorithms, in combination with a few, which turned out to be fairly minor hardware changes, ended up increasing system efficiency by up to 7 times at the top of the pipeline, 8 times at the bottom of the pipeline. And something I didn't tell you about was we were able to improve rasterization by another factor of 3 to 11 in the middle. So this was a collaboration of myself and some colleagues at Stanford along with industry. And the thing that I took away from it, sort of coming from a software person, was to think about solving problems in systems by thinking about algorithms, hardware, as both fair game. And at the end of the day, by changing both of these, we were able to preserve these abstractions that all systems are built on. Okay, so I wanted so that was section 2 of the talk. Section 3 is brief, but there are a number of tough questions that are arising. So here's the first tough question, is that we have been the victim of our own success in computer graphics. And that success is because we had the right abstractions. We could go off as architects and implement and innovate very, very aggressively in terms of parallel systems. If you had to program these types of systems in C or C++, they would be unwieldy for people to get good performance out of. But if you program them with the graphics pipeline, it becomes very, very tenable. In fact, we can teach OpenGL on the graphics pipeline in undergraduate graphics, and those programs make excellent use out of fairly exotic machines. Now, that's been really good. And what that's enabled is it's enabled us to build really, really fast machines. And now that we have really fast machines, it means that more advanced techniques, things that we never thought would be feasible in real time, such as actually micropolygon rendering only about a decade ago, are now very feasible. Like real-time ray tracing is not a far-fetched thing. It's literally been demonstrated, and it's a viable option for future graphics systems. Things like global illumination, complex lighting, and especially if you look at like what Adrian does, real-time physics are all things that can be done or will be or potentially can be done very high fidelity in the near future. Now, The problem with this is that the domain, the space of things that we can do in real time is expanding, which is putting a whole bunch of pressure on these abstractions, which is the whole reason why we were here in the first place, is using the graphics pipeline as a mechanism to express this wide variety of techniques, these wide variety of applications, is not the best thing to do. And so the big question that I deal with on a day-to-day basis, and many of my colleagues deal with, is answering the question is, what is the future of this programming model, or of this abstraction? And a lot of people, algorithms people, are saying, let's just scrap it. Give me one of these exotic machines in a C compiler, and I can do whatever I want to do. And other people are saying, no, we need to stay within the structure. So the question is, do we evolve, such as what I have done in the last couple of years in my work, or do we just scrap and ultimately completely replace? Now, this is a question that I think a lot of people in their own respective domains, for example, you guys are probably facing in your own performance-centric computations, whether it be like machine learning or computer vision, mobile devices, and things like that. And an area that I've actually gotten really interested in recently is, in fact, cameras. So before I came here, I spent 9 months working at a camera company. And that camera company, well, I'll tell you about that actually in a second. But the reason why I've been interested in cameras is, for me, as an architect of these visual graphics systems, I see cameras as being cheap, ubiquitous sensing. They're getting smarter, in that graphics was not a very programmable thing. It was a very fixed function thing 10 to 15 years ago. Now cameras are going through that transition like graphics was 15 years ago. People are wanting to do more with their cameras, want to do more with processing the images. They want to be smarter. They want to recognize faces. They want to do computational photography and blend a bunch of images together. And a lot of these techniques about being smarter are actually highly dependent on big data from the cloud. And so a lot of algorithms that used to be very, very hard now become tractable and possible if you have large databases. So I see this as an instance of another domain, very much like graphics, that's just sort of looking for structure. And the reason I got into this actually was the last couple months what I've been working on. I've been working at a company called Lytro. Adrian mentioned it. But Lytro, we've been developing planoptic cameras. Is anybody familiar with like sort of the concept of the light field camera? A little bit. You might have seen this. The main idea is that our cameras, what they capture is they don't capture images. So at the end of the day, with a traditional camera, you get a 2D array, and it has a magnitude at each position in the image. What these cameras capture via a change to the optical system is they capture a representation of all the light, the rays of light that enter the camera. So our data set, when you press the shutter, is in fact a list of rays. So color in this direction at this position. Okay. So if you have that information, you can use very standard computer graphics techniques, right, to trace the rays to where they would have gone in any other camera system to produce many different types of pictures. So we can refocus the picture in software after it is taken. We can do things like change the parallax or the actual position of the camera by simulating where we were in some virtual aperture. Okay. So you can imagine that the computational requirements of this camera might get really high. And they are getting really high. We acquire more data. We have to do more compute to generate an image. So one of the things that we've been thinking about, and we've been thinking about this in the context of photo sharing, is that even in the simple thing of taking a picture, you've got to take a picture off a very high bandwidth sensor. And that picture is not very useful until it's on Facebook, to be honest. And so we've been thinking about problems of, okay, you need to sense, you need to process, and then you need to also leverage the cloud. And I see this as sort of a photography example of many of the same problems that we're faced with today in sensing of many different types, whether it be image sensing with cameras or acquiring data in other forms. Making some decisions about doing processing either on the sensing device or on a mobile phone or something tethered right next to it, and making decisions about what actually needs to happen out in the cloud. And so some of the questions that I'm interested in are things like, where does this compute occur? And what are the cost, power, and sort of user experience latency trade-offs of doing it at various places where I can stand in this ecosystem? Another question that I already mentioned to you guys is, what is the level of programmability required for these systems? And it might be very different for someone who's trying to write applications to produce beautiful pictures for photography versus someone who's trying to write applications that's trying to do computer vision in real time on some mobile device. And especially in the computer vision sense, I'm very interested in what are the key abstractions and primitives in these other spaces. So what is the equivalent of the vertices, fragments, and triangles in some of these other domains? And if we could establish that, could we really begin to innovate in the systems that we can provide you guys for doing that type of work? And last, I think the answer is sort of yes, but in what form I don't know, is how fundamental will be the cloud in actually, not just the algorithms, but actually in the processing systems. Is should I give you a computer without giving you a mechanism to connect it to the cloud? And so here you're starting to see a pipeline arise, which is very much like, in some ways starts to remind me of the structure and the data flow of vertices and fragments and pixels going through the graphics system. So those are the things that I'm interested in. I tried to give you a little bit of a flavor of sort of how in graphics, how we have optimized the heck out of these systems and how we think about them as sort of high-level architectures. I definitely am getting kind of interested in sort of how we might recreate some of that in vision or in image processing. So I'm at 45 minutes, so that's exactly where I wanted to be for this talk. So. Questions? Adrian.
So I think this idea of like of inverse graphics or like vision pipeline, the same kind of like abstractions and also the same kind of optimization opportunities that graphics offers is really cool, but I can't think of what the primitive operation is.
I can't either. But the claim that I would make is I'm not sure if people in these communities are trying to think of that, right? And I'm not a vision person. I do graphics. So I'm fortunate that when I'm building these systems, I can think really detailed level about what are the implications to my application domain in how I choose or adjust my choice of primitives. And I think the argument here is that I think, so what's going on right now? What's going on is that vision, these guys are jumping, they're really excited, right? Because all of a sudden NVIDIA is producing Tegra, which has an image processing chip and these GPUs, and everything's right there in the mobile space for you. It's the first time you've had abundant processing power in mobile. But what's the reaction been? The reaction has been to take OpenCV, which is a big library, a grab bag of techniques, and just accelerate some key kernels. And the observation that sort of we have in graphics is that's not how we built these systems. We actually came up with systems where we sort of made the programmer think in a certain way, and that was the key to the optimization, which is sort of different than optimizing all these black boxes and then just kind of throwing them out there and seeing what happens. So it's a little bit more powerful way of thinking, and it may not apply. Vision and these domains are really broad. At least in graphics, we can say, at the end of the day, we have a model, and we want to produce an image from the model, right? It's a fairly constrained problem. You could argue, and I think you might be able to argue correctly, that vision is much more broad, and so maybe the strategy is a bad idea. But at the same time, I don't know, and I don't know if anybody's really taken a good look at it to be certain. I do know that in graphics, now we're coming to the space where graphics is now broadening out. And that's why we're having this big debate about what should we do in graphics as well. And I think that debate could be had in some of these other fields that are very compute intensive today. Because we're trying to figure out how to build these chips and architectures for the domains that are going to use them the most. And graphics is influencing that domain, and not a whole lot else is right now. And I think you might want to be involved in that conversation.
I think if you narrow down the focus in vision to, you take the input as a bunch of images and your output is a bunch
of features, right? Yeah, I've heard that.
Whatever it is. So if it's images to features or images to images, then that pipeline usually can be well defined. What you do with those...
Right, it seems like at that point it's so application specific. Yeah, I agree.
The tasks are really broad and may not be parallelizable, and people have, still have...
And it's just a free-for-all at that point, right? Now, in graphics, we have that. That's the shading model, right? So we've sort of we've sandboxed that part out and said, you know what? You throw your code in here subject to a few constraints. We don't have any idea what's going on in there. There's no concept of a light or material in a GPU anymore. It's you do whatever you want. And that part of the vision problem to me sort of is the analog of that. Right. But that still does fit within some structure. And the structure still, to this day, provides an insane amount of value in scheduling these things and using all these resources. So I don't know. I think it'd be interesting to take some experts in those areas and really dig in and see, is there something that we could do here that's better than just saying, give me a big multi-core and give me an ASIC that does face detection or something like that. Like, I think it would be an interesting exercise. It'd be a great class project for somebody in my class, but so I'm trying to encourage people to do, but yeah.
So by the way, in your triangle optimization, if you think about sampling in terms of rendering, if you think about depth of field.
I think I know where you're going with this, yeah.
So you have a lot of blurring and you're looking at
Yep.
wider areas. But very counterintuitively, you're actually doing much more sampling to create a blurred effect. You see what I'm saying?
Oh yeah, yeah.
Lots of things,
Yep.
like even when you're rendering volumetric scattering, you have to do a lot of computation to create a blurred image.
Right, so to summarize, I think for everybody, this is one of the things in graphics that's an unfortunate tenet is that things that are very imprecise, such as simulating the defocus blur of a camera or simulating the motion blur, tend to be computing integrals. And to compute these really imprecise things, we have to burn a lot of computation, right? So we end up sampling at a really high rate to compute a high dimensional integral with low noise, right? So it turns out the blurry stuff tends to be the hardest stuff to compute. There is a lot of work in the last year or two, in the past, and that's kind of all kicked up again in the last year or two, was where the paper that I didn't talk about, the middle phase, was we did an analysis of some of this stuff, and we said current algorithms are extremely inefficient. And so people have been trying to look at how to make that more efficient. I'll give you a couple examples. Like, for example, if we know the surface is going to be blurred, because we're going to render it with a camera that's out of focus in the background, why in the world are we tessellating it to these really high resolution surfaces, right? But it's not quite as simple as one might think, because all of a sudden, what if the brightness of the surface comes from the specularity, and all of a sudden when you smooth that surface out, you lose all the specular highlights. So there hasn't been any good, robust, in all situations way to do this. There are other people looking at it completely in the Fourier domain and basically trying to come up with data-dependent reconstruction filters so that you change the shape of your reconstruction filter on these sampling problems with some prior knowledge of the signal that you're actually trying to sample. So for example, with motion blur, if you know you're blurring this way across the screen, all of a sudden you're going to want to extend your filter support far in this direction to reduce noise, because there's no detail in there that you're going to lose anyways. So it's been pointed out many a time. Robust solutions to it in all the cases are hard to come by. Solutions that work in certain cases are very easy to come by and very effective. So they work in film. They don't work in real-time stuff often, because in film you can take a look at the thing you rendered and you say, does it look good? Okay, if it looks good, go ahead and ship it out. In interactive stuff, you need to build algorithms that work most of the time under a large space of possible configurations that a simulation could be in. And so we don't have a lot of stuff we're super comfortable with yet. Yeah, but there were like 2 SIGGRAPH papers on this topic this year, actually. Yeah, all frequency space, trying to figure out how to take a small number of samples because you know it's blurred, so you know there's no frequency content there. And then the problem with that is you have noise, and you try and knock out the noise or the variance in the Monte Carlo estimate by using a data-dependent expansion of your reconstruction filter in some way. Yeah, hot topic right now, very hot topic. Yeah, what's up?
You motivated your talk by saying you wanted to reach real-time
Yeah.
Pixar graphics. How close can you say you kind of reach that?
We can do, well,
It's like 3 or 5 or 8 times reduction in.
yeah.
Is that?
We can do, we meaning none of this stuff is built, but I expect some of these ideas to go in future GPUs in the fairly near future. Let's say they do some of these things, some subset of these things. At that point, you're a pretty darn good system for rendering micropolygon, almost film quality characters in real time, but you're not going to get the high quality lighting and shading yet. The full global illumination solutions continue to be out of the realm of real time. But you kind of need to get the high resolution surfaces first. Because I have examples in sort of my more graphic specific talks is you put really high quality lighting and shading on a low resolution model, all of a sudden texture mapping alone isn't good enough to hide the low resolution. So I think you need to have the high quality surfaces first. Then you compute the advanced lighting and shading, which we don't have the best fast algorithms for yet either, using the high resolution meshes. And then you're getting close. But in terms of characters, I think we could do a really nice looking film quality, Finding Nemo set of characters with some of these optimizations within the next 5 years. The problem is that film scenes mean that there's another 100,000 fish in the background, right? And so that kind of stuff I think is quite a large way off. It's like the world complexity. But in terms of if I tried to put you on the screen and render you, I bet I could do that pretty soon. Yeah. Laser scan you. Yeah. All right, thanks guys.